Hey, have you ever picked up a tool and just felt stronger? Like you suddenly had superpowers? Well, today we're going to crack the code of simple machines. These are the genius devices hidden all around us that multiply our strength and make seemingly impossible tasks, well, possible.
Okay, so think about this for a second. Scissors, a bottle opener, and a fishing rod. I mean, what could those three things possibly have in common? They seem totally random, right? But believe it or not, they all share a powerful secret, a fundamental principle of physics.
And here it is. They're all simple machines. And we're not just talking about tools here. These are like our secret weapons for multiplying force, changing direction, and even gaining speed. So let's unlock the genius behind how they all work. So how exactly do these machines pull off their magic tricks? It really boils down to four main ways they help us out, turning a really difficult task into something you or I can actually manage. Okay, so machines give us four key advantages. First, they can act as a force multiplier, right? Just think of a jack lifting a whole car. Second, they can change where we apply our force. Like on a bicycle, you push down on the pedals to make the back wheel go forward. Third, they can totally flip the direction of our effort, like pulling down on a rope to lift a heavy bucket up from a well. And finally, with something like scissors, they give us a gain in speed, turning a small squeeze of your hand into a quick, long snip. Now, if we really want to understand how these machines give us these superpowers, we've got to learn to speak their language. And don't worry, it all comes down to just a few key terms that describe the forces at play. First up is the load, which we usually just write as a capital L. This is simply the thing you're trying to move or fight against. It's the heavy car, the stubborn bottle cap, the weight you're lifting. It's basically the resistance. And on the other side, we have the effort, shown as a capital E. This is your contribution. It's the force you put in. It's you pushing on the jack handle, squeezing the nutcracker, or pulling on that rope. It's the work you do on the machine. And this is where it gets really powerful. When we compare the load to the effort, we get what's called mechanical advantage, or MA for short. This little number tells you exactly how much the machine is boosting your strength. So an MA of, say, 5 means the machine is making you 5 times stronger. How cool is that? Then you've got the velocity ratio, or VR. And this one is all about speed. It compares how fast your effort moves to how fast the load moves. Think about reeling in a fish. You might turn the handle really fast and move your hand a long way just to pull the fish in a little bit closer. That's a high velocity ratio in action. So how do force and speed relate to each other? Well, it's all through this idea of efficiency. Efficiency, which we show with the Greek letter eta, tells us how well a machine is converting our effort into useful work, and you can calculate it simply by dividing the mechanical advantage by the velocity ratio. That's the golden rule. Now, in a perfect world, we'd have these ideal machines that are 100% efficient. Every bit of work you put in would come out the other end. But, we live in the real world with real machines, and in the real world, there's always friction. The moving parts rub together, and some of that energy gets lost, usually as heat. That means a real machine's efficiency is always going to be less than 100%. Okay, let's type into our first major type of simple machine, the lever. A lever is really just a stiff bar that pivots around a fixed point. We call that point the fulcrum. And it's all about this incredible balancing act between your effort, the load, and that central pivot point. And here's a fantastic little trick to remember the 3 different classes of levers. Just remember the letters F, L, E. For Class 1 lever, the fulcrum, the F, is in the middle. For Class 2, the load, the L, is in the middle. And for Class 3, you guessed it, the effort, the E, is in the middle. FLE, 1, 2, 3, it's that simple. This table really lays it all out for us. For Class 1, with the fulcrum in the middle like a seesaw, the mechanical advantage can be pretty much anything. But check out Class 2. With the load in the middle, the MA is always greater than 1. That means it's a true force multiplier. Then you have Class 3 with the effort in the middle, where the MA is always less than 1. This one's a speed multiplier. Let's look at a few examples. Class I levers are the great balancers. They put that fulcrum right between your effort and the load. The seesaw is the classic example we all know, but a pair of scissors or pliers are also perfect examples. The pivot is right there in the middle. Next up, Class 2 levers, where the load is stuck in the middle. A wheelbarrow is a perfect example. The wheel is the fulcrum, the heavy stuff you're carrying is the load in the center, and you apply your effort at the handles. And like we saw in the table, these are always force multipliers. They always give you a mechanical advantage greater than 1.
And finally, we have Class 3 levers, where the effort is applied between the fulcrum and the load. Think about that fishing rod again. The end of the rod tucked against you is the fulcrum, you lift with your hands in the middle, and the fish is the load at the very end. With these, you actually sacrifice force for a huge gain in speed and range of motion. A tiny little movement of your hands creates a big, fast whip at the end of the rod.
All right, let's move on from levers to another incredibly useful machine, the pulley. A pulley is basically a wheel on an axle that's designed to let a rope move smoothly over it. These are the secret to lifting really heavy things with what feels like no effort at all. Now, a single fixed pulley, like one you'd see on a flagpole, doesn't actually make you stronger. Its mechanical advantage is just one. Its real genius is convenience. It lets you pull down to lift something up. But a single movable pulley, one that's attached to the load itself, that's a true force multiplier. It basically cuts the effort needed to lift something in half, giving it an ideal MA of 2.
But the real magic happens when we start combining pulleys into a system called a block and tackle. And the rule here is just unbelievably simple. The ideal mechanical advantage is equal to the number of pulleys in the system. So if you have 5 pulleys, yep, you're 5 times stronger. It's just that powerful.
Okay, you've learned the code, you know the secrets of levers and pulleys. Think you've got it down? Let's put that new knowledge to the test with a quick challenge. You ready? All right, first one. Think about a wheelbarrow. The heavy load is in the middle, the wheel is the fulcrum, and your hands provide the effort. So what's our mnemonic? FLE for 1, 2, 3. What's in the middle here? The load. That makes it a Class 2 lever. Exactly, a force multiplier.
Okay, one more. You're using a fishing rod. Your hands, that's the effort, are between the end of the rod, the fulcrum, and the fish, the load. So, using our rule, what's in the middle? The effort, which means it has to be a Class 3 lever. You're trading force for that awesome gain in speed.
And there you have it. You've officially cracked the code of machines. From now on, you won't just see a bottle opener or a bicycle, you'll see the physics behind them, making your life easier. So now that you know, go look around. Find the machines that are hiding in plain sight all around you.